Hello everyone. In this video, I'm going to discuss to you the dynamometer operation. Now, the brake or the dynamometer operation in the lab bolt 8960 module, 4th quadrant, is a machine which can be coupled to a motor using a timing belt. As you can see from this figure, we can couple it with a DC motor, which will be used as a power supply, as a prime mover. And this will be our mechanical load, and we are using it as a brake, right? We can also adjust the torque load of this of the brake by the control knob. So the brake also measures the speed and the output torque. So another function of this module is to measure the speed and the output torque of the motor. In other words, it acts as a brake as well as a speed meter and dynamometer at the same time. So it has two functions. The mechanical load of the motor can be changed using a torque control knob of the 4-quadrant dynamometer power supply. Where is that torque control knob? This is the torque control knob. We can increase, so we are controlling this torque. We can increase the torque load of this machine that has to be shouldered by this DC motor. We can increase or vary the torque load using this command knob. Okay. In the previous experiments, if you can still remember, as a prime mover, when we use this machine as a prime mover, here is our connection. Lab bolt X960 is used as a prime mover, and this is a machine load. In the previous experiment, we used the induction motor. So we noticed as a prime mover, the display on the 4-quadrant machine allows direct reading of the speed and the torque. What did you observe from the previous experiment? We can see here, while it is running, we can see here when we set this to not corrected, clockwise direction, prime mover, brake, prime mover, clockwise direction, we can see here a torque which is a negative value, which is negative, right? Negative torque. Okay, so this is actually the actual torque. Okay, now as a prime mover, the display in speed, the display speed on the module display or the speed meter in the metering window are the actual speed at which the brake rotates. It is positive for clockwise rotation and negative for counterclockwise rotation. Okay. Now, question: will the display screen of lab bolt shows the same when we use the machine as a dynamometer brake? Will it give us the same negative torque here on this point, or a positive torque? So in this case, as a prime mover, it is showing here a negative torque when we set this one to not corrected clockwise here, clockwise. So it shows a negative torque here, right? Now, the total mechanical load which the brake that the dynamometer produces when it is coupled to a motor consists of course, the friction, the belt friction, which you're already aware of. We discussed our last experiment. The friction on the dynamometer. What are those friction? The bearing friction, brass friction, the windage friction, and also now we have a magnetic torque, right? The magnetic torque which the dynamometer produces to oppose the rotation. This magnetic torque is controlled by we can adjust this magnetic torque by a command knob, right? We can control the magnetic torque by a command knob. So the total the equation for the total load will be torque friction of the belt, torque friction of the dynamometer due to the brushes, bearing, and windage, and the magnetic torque of the dynamometer. Question is it a T corrected or a not corrected? So let's proceed with our discussion. Now, as a dynamometer brake, the display torque of the displayed torque for clockwise positive rotation is positive. What does it mean? If my direction is clockwise, the displayed torque here will give me a positive value, right? When you set the second quadrant constant torque brake NC, this is also a not corrected. You can see here, let me show you. See here, 2Q CT brake NC, and it will give us here a positive torque. That's what it means. For counterclockwise or negative direction or negative, the displayed torque is negative, right? So when the rotation is counterclockwise, it gives me negative. When the rotation is clockwise, it gives me positive. Or in other words, the torque and the speed displayed are always same polarity. To summarize what we have mentioned here, the torque and the speed are the same polarity. Is it the same with the prime mover from the previous experiment? From the previous experiment, it's different, right? From the previous experiment, when we use it as a prime mover, you see, okay, we have here a negative value of the torque, right? When we are counterclockwise, the torque here is negative, it's opposing when we are using it as a prime mover. Now we are using it as a dynamometer. It is showing that the torque and speed have same polarity. As dynamometer and brake also, when the command knob is set to minimum or fully counterclockwise, the magnetic torque of the brake as a brake is zero. Therefore, the torque indicated here must be zero. The torque indicated here must be zero. So the output here, meaning to say we are measuring here the magnetic torque. Always the magnetic torque should appear here. When we set this to non-corrected torque and this positive, it should show the magnetic torque, not corrected. Now, the torques, due to the belt friction and the frictional torque of the brake varies with speed, right? So it can be very, very small at very high speed. So, but the torque of the magnetic torque does not vary with speed. It can vary only using the control knob. We can vary it from 0 to 3 Newton meter using the control knob. We can vary it to what? 0 up to 3 Newton meter. Okay? 0 up to 3 Newton meter. It doesn't change with respect to the, it doesn't vary as the speed varies. Okay? So that's the difference. As a dynamometer or brake, the torque indicated on the display for the 4-quadrant dynamometer power supply and the torque meter in the metering window has the same magnetic torque, but it is opposite polarity. So, what does it mean? It will give me a negative polarity. Okay, the indicated torque will be equal to a negative of T magnetic of the brake, equals to the torque of the motor coupled to the brake. This is the torque that the motor must provide to overcome the opposition to rotation caused by the magnetic brake. So what does it mean? So that much the motor torque must have a total or absolute torque to overcome the magnetic torque, the brake, the belt friction torque, and also the frictional torque of the friction of the dynamometer itself, torque friction of the motor itself. So it should overcome, right? So what will be the total? What will be the equation for that? So we have the T out, right, is equal to the T load is equal to the negative of the overall torques that we have. We have the magnetic torque, torque friction due to belt, and the torque friction, windage, and the brushes, and the bearing. Okay, so this is the corrected torque. Okay, this will be the corrected torque. The corrected torque will be the total torque of the magnetic, the belt, and the torque friction, internal torque friction. So what can you say about this? We can say that the corrected torque is always greater than the not corrected torque when we are operating this as a brake or as a dynamometer, right? So the corrected torque is the total torque, the absolute torque. Let's capital T, the total torque being provided by this motor to overcome all the load torque, right? From the belt, magnetic torque, and the torque friction, and the frictional torque of the machine itself, of the dynamometer itself. Okay? So we can again conclude that the T-corrected torque is the total output or the absolute overall torque delivered by the motor, which is the T out. Okay? Which is negative. It should be opposite. It should be negative. It will appear here. It will appear here positive, but it should be negative when we write the value. It should be negative. Okay? Let's say in the exam, what is the torque? It will appear here positive, but you have to write negative value. Right? This is the total opposition torque carried by this.